tell where a function is increasing or decreasing, which means we're getting really close to being able to tell whether a function has a max or a min, relative max or min, without ever having to graph it. We're also going to learn this new concept called an antiderivative. Doesn't that sound exciting? And how to find the equation for a function if they give you its derivative and a point, and we're kind of going to work backwards. The first part, knowing where a function increases or decreases, very, very important because it helps us tell what's going on with the graph without graphing it. Antiderivatives are kind of the baby step before integrals, which is what all of second semester calculus is about. So it's kind of a big day in calculus. So the first thing is we just got to write. This whole increasing and decreasing thing is not really brand new. We've talked about this a lot. Talking about how do the derivatives relate to when a function is increasing and decreasing, but maybe we just haven't written it out step by step. But notice, this starts pretty much the same way that mean value theorem starts. It has to be continuous on the interval and differentiable on the open interval. Because if that's not true, then you might not be able to say that it's increasing or decreasing the entire time. But do you remember what we talked about looking at a function when it's increasing? What do you know about its derivative when a function's increasing? The derivative is positive because the derivative equals slope, and if the line is increasing, it has a positive slope, and if the line is decreasing, then it has a negative slope, and if the line is constant, it has a zero slope, and that's kind of where we're going with this today. So it says, what? No, this is like things about increasing and decreasing functions. Like first thing. 1, if the derivative is greater than 0, or if the derivative is always positive over a specific interval, then we can say we know the function increases on that slope. And conversely there, if the derivative is less than 0, or if the derivative is negative, we know that means that the slope is negative, so that means that on that interval, that the function will be decreasing. Where does a function change from increasing to decreasing? At a max or a min. Do we know how to find possible max or mins without having to graph it? Critical points, set the derivative equal to 0, which means if we're trying to break up a graph into intervals of increasing and decreasing, we can use those critical points and then test to see whether the derivative is positive or negative. So we're going to be able to get a little bit closer to telling what our graph looks like without graphing it. Oh look, we just answered that. Where does the graph change from increasing to decreasing? At relative max and mins. AKA critical points. Why am I using blue? Is the real question. You're gonna stay up super late tonight to watch the election results? Super late. You're gonna have to stay up super late. I'm going to bed. Late. Yes.
I don't see what the difference is between staying up till like 2 in the morning and just getting up at 6 and watching it.
Stay up sooner.
Yes, I do.
Yeah, all I'm gonna do is set the alarm for 2, check my Twitter, and be like, okay, I go to sleep.
I'll just wait till I get up in the morning. You might know some local stuff earlier than 2, but the president, like, because of the West Coast and everything, and the time difference, and then they have to count the votes, and, like, because some people, don't vote electronically. Like me, I filled in a little marker this morning and connected my arrows, so they have to count the votes by hand. That's how I voted.
Maybe they use it kind of like a Scantron.
Well, no, I put it in this little machine, but there's no way that it counts it. I don't think so. I would be very.
Well, those people who count votes have to be very trustworthy.
I know they could just lie,
Did you
right?
guys hear about the girl at the top? What she did? There was this girl at the top, who registered to vote here in Putnam County and also registered to vote in California. That's all it's paper. So she would vote twice, and now she's getting press charges on for.
Oh, I heard that. I didn't know it was DePaul, but I heard there was someone that was like arrested for trying to
It
vote
was
twice.
on the front page of the Banner Tribune yesterday. That's right.
Today, I heard someone got killed in Cloverdale on a bad drug bust, on a bad drug deal. Yeah.
Yeah, Wendy's caught on fire.
Oh my gosh, we're famous.
Okay, guys, focus.
We're famous. And we're getting a parking garage too. In Greenhouse.
My goodness. Notice the directions. Find the local extrema and the intervals where the function is increasing or decreasing. So we found local extrema before, relative max, relative mins, but now we're going to throw in the increasing and decreasing. What do I need to do first if I'm finding extrema points? Derivative. And look at a nice little function I gave you. What kind of teacher gives you such easy work? What is the derivative of this? Once you find the derivative, if you're trying to find critical points, you're looking for where it equals 0, where it's undefined. Is this one ever going to be undefined? No. First of all, this is a parabola. Second of all, the derivative is a straight line. There's no undefined point, so we're just going to solve this. Get 1 equals 2x, x equals 1/2. Agree with me on that? So let's talk about how we can use this increasing and decreasing stuff to help us find local extrema points. If this is a possible local extrema points, that's going to be our dividing point for our intervals of increasing and decreasing, because if this is a max or a min, one side's going to be increasing, one side's going to be decreasing. What's the domain of this function? All real numbers. Do you agree that a parabola just has one, like a max or a min? Probably can kind of get there without actually doing this, but we're going to break this up. We can say that we could break this up into two intervals. Our graph is going to go from negative infinity to 1/2, because my domain is from negative infinity. Why am I stopping at 1/2? Because that's a critical point. That's a turning point in my graph, right? And then I could say from 1/2 to infinity. We can include them. It's kind of this whole big debate in calculus. Do you include the endpoints or you don't include the endpoints? I don't like to include them because what is the derivative at when x is 1/2? What is the derivative? 0. So is it increasing or decreasing at 1/2? Do you agree that it's 0 at 1/2? Does that make any sense what I'm saying there?
So we like row.
Right, and the thing is, the book kind of changes back and forth. Every book is different whether they include or not include them. I don't usually include them because I feel like it equals 0 at 1/2. It's not included. But the AP exam would never count you off for including them or not including them on a free response. And on a multiple choice question, they would never give you options where one option was this with it out included and one option was with it included. They would either always include it or always not include it so that you wouldn't get confused by that. Does that make sense? And so I'm not going to include it because I feel like at 1/2 it's not increasing or decreasing, so that's why I don't include it. If we want to check to see where it's increasing or decreasing using calculus and not just what we know about this graph, because this was the easy one, we just want to determine on this interval, is the derivative positive or negative? So basically I'm just trying to figure out what's happening here. So could I pick a number that's in between negative infinity and 1/2? 0. Is 0 in this? 1's not in this, right? Do you agree with that, Stephen? 1 would be over here. Okay, just checking. So I'm going to just check what's happening at f prime of 0. At f prime of 0, oh sorry, g prime of 0, failed by me. Plug that in over here. When I plug 0 in, do I get a positive number or a negative number? Because 0 minus 1 is negative. Do you agree with that? Anyone have any clue what I'm doing here? If on this interval the derivative is negative, what do I know about this graph from negative infinity to 1/2? It's decreasing, right? Negative means decreasing, so I can say I know this is decreasing. Which means, probably we could guess what's going to happen over here. If I pick a point bigger than 1/2 to infinity, you can pick whatever you want. Pick 700 if you want. I'm going to pick 1. And if I plug 1 into my derivative, not the original, I'm looking at the derivative because I'm thinking about slope. If I plug 1 in there, do you agree I get a positive number? Which means my graph is increasing. So if my graph changes from decreasing to then increasing, does that mean 1/2 is going to be a max or a min? If this side of my graph, so let's pretend here's 1/2. If this side of my graph is decreasing, and then at 1/2 it changes to increasing, can I tell if that's going to be a max or a min without graphing it? Yeah, because decreasing to increasing, that looks to me like that's going to be a minimum of that graph. I picked a really easy one to start. We could have told all of this without graphing this. Do you know which way this parabola opens? Up, which means it has to have a minimum, not a maximum, right? And if it opens up, does it make sense that the left side of that graph is decreasing and then it changes to increasing? Don't be afraid to use a little algebra to get your answers here. But I think that we should say here, as our answer, that we have a minimum at 1/2. We still have to find what goes with that, right? When you plug 1/2 in there, do you get 0? I don't think that's true. Doesn't necessarily, it's not necessarily going to be on the, like the vertex is not necessarily going to be at this minimum. Do you agree with that? Like, it's not going to be the y-intercept is what I'm trying to say. Like, if I plug 1/2 in here, what's 1/2 squared? Minus 1/2 minus 12. It's almost 12. 1/4 minus 1/2 is negative 1/2. Negative 12 and a fourth. Negative 12 and a fourth. And then you also need to tell me the intervals of decreasing and increasing. So I'm going to say it is increasing on the interval from 1/2 to infinity, and it's decreasing from negative infinity to 1/2. And again, if you included the 1/2, it wouldn't be wrong.
Wait, why is it a maximum?
One, we only have one critical point, right? And we have to determine, is it going to be a max or a min? Well, we know this is a parabola that opens up. Is there going to be a maximum on that graph? No. Only a minimum. Say it. What do you think? No, you have to put negative infinity first, because it's smaller than 1/2. And the smaller number always goes first, right? Let's see if I have another one of these. I'm not sure if I do or not. Oh yes, I do. Same direction. This is the same as 2x to the negative 1, yes? So if I start with my derivative, bring down the negative 1, so that's negative 2x to the negative 2. So that would be negative 2 over x squared. Where's that going to equal 0? If I tried to solve this, wouldn't I multiply both sides by x squared? X squared times 0, I'd get 0 equals negative 2. What else do I look for with critical points? there any place where that derivative is undefined? Before we think about increasing and decreasing, for extrema points, what happens when I plug 0 back up there? It's undefined, which means is that going to be a max or a min on my graph? So it's undefined. But critical points can still break your graph up. Like it could still change from increasing to decreasing. Think about, do you know what this graph looks like? It's a number over x. So the asymptote, like the L-shaped graphs, that's what I like to say, like one side goes like this, and one side goes like this. Which means one side could still be increasing, one side could still be decreasing. The directions still say it gives intervals. Maybe the whole graph is increasing. We still got to do that. This 0 is still going to be our breaking up point because although it's not a point in our graph, it is an asymptote on our graph, so it could change. So I'm going to show you another way of doing this. Maybe you don't want to set the intervals up right away. If this is your critical point, you can kind of set up a little number line and say, okay, I want to look to see what's happening on the left of 0 and what's happening on the right of 0. And remember, we're looking at our derivative. What's the number on the left of 0 that I could plug in? Negative 1. And so I'm going to plug in f prime, again, I use f, h prime of negative 1. And I want to know, to the left of 0, is that derivative positive or negative? Because it tells me whether it's increasing or decreasing. Here's the biggest thing to remember. We're plugging this into our derivative, not the original problem. So remember that our derivative was negative 2 over x squared. So when I plug negative 1 in there, I don't really care the answer. I just want to know, is it going to be positive or negative? Negative 2 over 1 is going to be negative, which means to the left of 0, do you agree that we can say for sure that we know that graph is decreasing? And we're going to do the same thing on the right of 0. And you can pick any number you want. I'm going to just pick 1. And it's still negative, because when you square something, it's still going to be negative 2 on top, which means it's still decreasing. So there's a couple ways you could write this. Could we say this graph is decreasing over its entire domain? Why not? Yes, I feel like there's two answers to this. It does have an asymptote, so if we wanted to write it, we could say 0 is not really included, right? We could say it's decreasing from negative infinity up to 0. We definitely wouldn't include 0 on this one because it's not even a point on the graph. You agree with me on that one? And it's decreasing from 0 to infinity. But I think I agree with Morgan as well. Is this the domain of the function? Negative infinity to 0 and 0 to infinity? Which means if I said it's decreasing on its entire domain, the domain actually doesn't include 0. Like the domain is not all real numbers for that function. And so both of these would be appropriate answers. Because the point where it's not decreasing is the point that's not included in the domain. So I just wanted to show you that I think both of those were true. That kind of makes sense what we're doing today. Also, we were supposed to give extrema points. We already decided, we probably should write this, there are no local extrema. Because the one point that we found that could be was undefined when we plugged it in. Another way to tell is if it doesn't change from increasing to decreasing or decreasing to increasing, there can't be an extrema point. Okay, so you're pretty much, your homework is broken into two parts, and the first part is all this stuff. Finding the critical points, but then doing the increasing, decreasing stuff. And then the second part is the antiderivative, and we're going to skip this next one. Okay, here we go. Antiderivative. It's like how you were when you first learned derivatives. You were because capital F of x is the antiderivative of lowercase f of x. basically, antiderivative is not the hating of derivatives, but it is the reversal. Like, if they give you the derivative, can you go backwards and find what the original function is? And we're just doing very baby ones right now because we're not going to learn all the rules for this right now. But it's kind of a good little brain work to think about. If this was my derivative, what would the original function be? So it's kind of reversing the power rule, maybe reversing a trig function. And when you do this, when they give you a derivative and you find the original function, we call that anti-differentiation. And so this is the second part of your homework, which isn't so bad to do once your brain gets clicked into thinking about antiderivatives. Notice the directions say find all possible functions f with the given derivative. But basically we're just thinking about going backwards on here. And so this first one here says, well, if the derivative was sine of x, can you tell me what the original function was? Negative cosine. Do you agree with that? Because the derivative of cosine is negative sine? No. Yeah. Look, my head's not working here. So this would be negative cosine, and it's really easy to check your work on this because you can take the derivative of this and make sure it equals this. Negatives will cancel out. But here's the important part. All possible functions. How do you know the original function wasn't negative cosine plus 1? Could that have been the original function? Because what's the derivative of 1? What if it was negative cosine plus 7? Could it have been that? Could it have been negative cosine of x plus any constant function? So when we write these antiderivatives, when it says find all possible functions, we have to include that there could always be a constant added to that. And so when we write this, we're going to write plus c. And that big C just represents any constant, because when you take the derivative of a constant, it equals 0. I don't know. Could they write it as capital F of x equals F? Well, see, they wrote it as this as capital F, but I didn't write it right. That one should have been capitalized probably. But that's okay.
Oh my god.
It's alright. Don't worry about that. Oh my goodness. Look at this one. Okay. Right, we can start with the end. That would be the easiest, right? Definitely, when you take derivatives, you lose an exponent, right? You always subtract one. So if we're going backward, we should be adding one, right? So if this was x squared, we would need x to the third in our original. Do you agree with that? When we take the derivative of that, do we get this? Yeah, so I don't have to worry about that because the 3 is taken care of. This one is x to the first now, so I would need x to the second, and since that's minus, I think I agree with Sarah that that's minus x squared. Again, if you took the derivative of that, the 2 comes into play. And if this is just 1, that's just x. Don't forget to add your c. That's it. That's not so bad, right? No, it's not. It's really nice today. I like to build you up with antiderivatives. Well, they're not bad today, I'm telling you. Okay, here's the last thing with it. The only other thing they could do is they might ask you to actually find the function, which means they're going to give you a point. Like, so instead of finding all functions, where you put the plus c on it, we're going to actually find the one specific function for this problem. And the bell's going to ring in just a second, but I'm holding you hostage. Come again, they're just giving you the derivative. The difference is they're giving you a point. So instead of just having to do a plus c, you're going to actually be able to find c. Is really the only difference in this. So it's a specific antiderivative instead of a general antiderivative. Now, step 1 is still going to be, let's find our original function. And again, it's not so bad here.
Why did you spell it THRE?
Because I just didn't want to write CHROUGH. It's notes shorthand. It's like the drive-thru at the McDonald's is spelled like that. Because it's short.
It is.
Oh yeah, like it's spelled like that. Is that how it's supposed to be spelled?
No, this is not a real word. It's just shorthand. It's like, but it's okay to do that in our notes.
I never knew it was called that.
If this is x to the first, what is our antiderivative going to be?
X squared.
And that takes care of the 2, right?
Plus x.
Plus x.
Sine.
Minus sign of
Plus sine. Maybe I am.
And again, you can check this. The derivative of sine is cosine. So we do need the minus in front of that so that it would be minus cosine plus c. And if the directions just said find all solutions or all antiderivatives, we're done with this. But this one actually gives us some more information. They tell us find the antiderivative where this is the derivative and it goes through this point, which means is this an x and this a y? Can you plug those in for x and y and tell me what c is going to equal? And actually give me a specific one.
Wait, where's y?
This is x, this is y. Where's y, honey? Right?
Wait, so what do we do with the c value?
We just solve for it. So look, here's right. We get 3 equals 0 plus 0 minus sine of 0 plus c. How nice that is. Which means that c equals 3. So your final answer, you're just going to replace 3 right there. So your equation would be f of x equals x squared plus x minus sine of x plus 3, because you can tell me what specific constant would be there. Yes? We'll talk about these more. Let's see. If you don't have your assignment sheet, there it is. 15 through 24 multiples of 3, 30 through 36 multiples of 3, 43. Like 30 through 36 are antiderivatives, I do believe. So. Hey, for the sub today, 6,000 people. Yeah, I put your bell work on the desktop, so it says Calc Lab, and you just have to click on it, or you can click on it. It didn't say. No,
I get really weird though. There's like, trying to tell us about her life.
well, maybe they will.
Where's it?
I can't do much about it.